Okay, can you all hear me? Yes. So I would like to thank the organizers for the opportunity to speak about our results. And that is different from what has been happening here today in at least one important aspect, and that is we are interested in size distributions of objects that are evolving in time. So when you look at precipitation, rain droplets, and we know that in many clouds they are very, very small, but then these rain droplets grow, and once they reach the size of a millimeter, gravity kicks in and rain starts. So rain or precipitation, for instance, is an example where we are not only interested in size distributions and at extremes. The largest droplets are the ones that fall first, but in particular we are interested in how these size distributions evolve in time. That's the same when you look at dew. So why is that not coming now? So there it is. Yes. So this is a picture of a dew formation taken in the lab. And what you observe here is, again, the dew droplets grow. And we are interested in the size distribution of these dew droplets. Eventually that determines pickup of droplets. It determines their interaction with mist and a lot of other important parameters. So I am a physicist, so for me, this is a general question about droplets that are embedded in some environment. So these are three-dimensional droplets in three-dimensional air, three-dimensional droplets on a surface, three-dimensional droplets on a string, three-dimensional objects on a rough environment, a snipe fly here. And what you will see in the first part of that talk is that I will denote the droplet dimension as capital D, substrate dimension as little d, and then I would like to understand how that is evolving in time. I start with the dew. Three-dimensional droplets on a two-dimensional flat substrate. Okay, technically that's very important because all drying technology relies on that. If you want to collect water in arid environments, there's a huge technology coming up of collecting drinking water with that. It's a very old topic. It's 100 years old. At least that's the oldest references that I could find. There was a heated discussion about Rayleigh and Aitken in Nature, where Rayleigh held that every photographer judged of the success of the cleaning process of a photographic plate by the universality of the dew deposited from the breath. Aitken had a slightly different experiment, which looked different, and he said, I, on the other hand, think that the character of the deposit is greatly and generally determined by the impurities on the surface. They couldn't resolve that at the time. It took the upcoming of surface science and very, very careful analysis of surfaces to clarify these issues. And since that time, we know that it's a bad idea to breathe on a surface in order to figure out that it is a clean surface. I mean, I would immediately kick every graduate student out of the lab who tries that. And then the problem comes up again in the 80s, and there the focus was on something slightly different. And that's what the topic is about today. When you look at that, and this is MBE data, molecular beam epitaxy, where you grow tin on sapphire, you realize that these are very, very, very polydispersed distributions. There's a characteristic size of the largest droplets, changes in time. But then there's a very broad tail of the distribution to very, very small droplets. So it's this broad size distribution and how it evolves in time, which will be the topic of the first part of the talk. I had two students, Tobias, who was doing that experimentally. He looked at films of cling foil, glass, identified these droplets. In the end, he had a few terabytes of data, highly resolved. Typical pictures of him have something like 10,000 droplets. The data set that I will show have close to 10 to the 9 droplets that he measured one by one and identified their size. Johannes did simulations, so he repeated simulations that were done in the 90s, except with slightly more resolution, and he has a much, much better statistics. So this is a size distribution. You see we start with something reasonably monodispersed, and then there is a bump of the original droplet site which is growing in time, and there is this tail of smaller droplets appearing in the back. The same in the simulations, except with much less noise. And of course, in the 90s, people immediately saw that, and they had the idea, okay, one should try scaling analysis, dimensional analysis. So let us assume that this is a ripening process, and the pictures stay pretty much the same, except for a change of scale. So there's the typical length scale, which is the size of the largest droplets. It grows in time with the power law. And then there's a universal function f, which tells us about the shape of the distribution. There's a parameter s to the minus theta. For dimensional reasons, theta is a power law which is determined by the dimension of my problem. So the dimension of the droplets, dimension of the substrate over d. That's very easy to understand. S will be the volume of droplets to the 1 over d. That's the length scale, and the length scale, and so this is the length scale to the power minus d. That's because this is the number of droplets per unit volume S, and per unit surface area, because it's the number of droplets per unit surface area. So this is dimensional analysis. You plug that in, you ask that the coverage is finite, and you will also figure out what this exponent z is. Dimensional analysis, reasonably straightforward. People checked that numerically, but we have much, much better statistics now, as I said. So in the numerical data, we see that there are small deviations in the tails of the distribution. Otherwise, this thing goes to a nice universal distribution as expected when you plot this function f. So what you would do is you multiply n by s to the minus theta, and you plot it as a function of s over the size of typical droplets. That's exactly what is happening here. So that works reasonable. When you do that for the experiments, you end up with a mess. And I was looking very, very puzzled as these two students because I was not aware about anybody in the literature who had discussed these tails. I expected that they would be there, but I wouldn't have expected them to be such noticeable. In particular, I wouldn't have expected them that they completely dominate the distribution in all of the experiments. And then there's also this funny slope. That slope is old. It has been observed 20 years ago. People thought about it. And there is a very beautiful paper by Blackman and Bouchard where they looked into that. They discussed the lower cutoff of the theory, explained that there has to be a lower cutoff, set up renormalization group theory, where connected this exponent to the amount of white area in these pictures, which is area which is not covered by droplets. And they showed that this area should be decaying like a power law, and that exponent should also be universal and only depend on the dimensions. And their prediction is that power law exponent should be minus 1/4 for the problem that we have. Okay, the numerical data are these. This is with error bars. All of our error bars are within the symbols, and it is minus 0.3 rather than minus 1/4. This is the experimental data. I wouldn't necessarily fit a power law through that, but if I have to, what is wrong there? Okay, sorry. For some reason, there was, so the issue here is this is minus 0.16. I don't know where this number disappeared. So the important issue is this slope is almost a factor 2 smaller than that one, and it is very different from minus 1/4. And so what we checked is that the reason that the theory breaks is that they assume the Smoluchowski approximation in the theory, which is wrong. And we can test that in the numerics and in the exponential data. But the puzzle to me presently is that these two exponents differ by a factor of 2. So even when you say, okay, let us do that better now, and let us set up a new theory for that, then renormalization group theory, which would go for universal exponents, is not the right way to do it. There has to be something more tricky, and we are working on that. The other part of the data which has to be explained is the tails, so the cutoff. We related that to the droplet growth at small scales, and eventually there is a correction to droplet growth, which is just onto the surface of the droplet, which is a surface contribution along the rim. For the experiment, that is surface diffusion. People have been working on that in the last 6-7 years in Mainz, so they have worked out what this is. You can import their theory and you get a description of the tails. Here, this is a geometric thing, which is actually has been pointed out by Blackman and Brochard. So we took that. We understand these corrections, and then taking this into account and using the measured exponents, this cutoff distribution f of s turns out to become nice and flat. So we basically get rid of all the funny features of these distributions. And the even nicer thing is that when we were at that point, we could show that the numerical and the experimental data fall exactly on top of each other without need to fit anything. So there's no fit here. At that point, I just asked the two students, take your data, put them into the same figure. They did it. And a week later, took them quite a while to get a consistent data format. They came back, and they were even more surprised than I was. So what we have learned here, just by carefully going through that, is that there is a scaling theory which tells us a lot. There's universality in the cutoff functions for the large scales, even so the scaling exponents seem to be non-universal. There's some interesting new physics in that, and the physics of how much water is condensing on surfaces is strongly dominated by the surface transport of these surfaces, which is very, very important for the applications and for what is happening there. So that is sort of what I would like to do now also for clouds. I would design a nice lab experiment, think about it, and try to understand how the evolution, what type of physics contributes to the evolution of droplets in my experiments, and then try to give indications to people about what they should expect in clouds. And this one, yes, that's a correlation gap. So eventually, what you see is the biggest droplets are clearly the droplets which are residing on the surface for the longest time. So there's a first generation of droplets which initially are roughly the same size, and when they merge, there is not enough space in between droplets to squeeze new droplets inside. So once you have populated the surface for the first time, there is a certain time, a certain lag time, when no new droplets are born. And that is exactly the time that it takes to grow on this logarithmic scale over such a time scale. And subsequently, you fill the gaps, and this is what is coming from the gaps. So we understand what that gap is about.
Is there also a cutoff at smallest scales? Or?
That's what I say. I mean, this is a cutoff for small scales.
Okay, yeah.
This is a cutoff function for large scales. This is a cutoff function for small scales, and in between there is a power law. Okay, and we understand, we analytically understand, we understand this one. So this we know what these functions are. I know that it's a power law in the middle, but I have to measure the exponents, and I have no clue why they are not universal. I would have expected that at that point the old theory will tell me what the exponents are. I was very surprised they are not, but then I accepted that, and what I see is that the large scale cutoff function is universal. It doesn't know about how I drive my system. It's completely different for the numerics and for the experiment, and still it's exactly the same cutoff function. So this cutoff function is, the funny thing here is the cutoff function is universal, the exponents are not. I mean, typically that's exactly the other way around. You would expect that the exponents are universal and the cutoff function is system specific. So let us come to clouds. So when you go out into the countryside, you go hiking, then we all have seen clouds like that. They are there, they're a sign of very nice weather. They appear and reappear, their typical lifetime is half an hour. Next day, same place, pretty much the clouds look like that. And that's a sign, okay, I mean, here it was very heavy rain on the horizon. When that is happening close to you, you know that in half an hour or so, you are bound to see very, very heavy rain. So there's a typical time scale of roughly an hour where these droplets either disappear and then there might be new droplets at a certain other place reappear as a cloud, or where they grow to a size that is big enough so that the rain initiation starts. So what I would like to understand is now what is really the physics behind that. Can we do experiments where we understand what is happening here? Of course, that is important for understanding climate. I mean, this is the famous or infamous picture by now of the IPP report. And it is a multi-scale process which involves many, many, many different things. There's microphysics, which has a lot of chemistry going down to 10 nanometer scales. Once you have droplets, once you activated them, you have inertial particles. These inertial particles follow tracks in turbulent flows. They interact. They possibly collide. There's mixing of the supersaturation and the droplets. Then you can mix material from outside the droplets, and then there are patterns of clouds. So I assume that there are people in the audience here who know much more about this part of the story than I will know in the near future. I'm very happy to learn more about it. I decided to contribute here. So we're in the process which is generating the droplets, and which is setting free very tiny droplets and deciding about whether they evaporate or whether they grow to a size which is important for rain formation, for precipitation. And I decided that we wanted to have to strip down the problem and go for the basic physics. So for me, the basic physics is that you look into a small piece of the cloud. It can be handful, and I would like to follow that and see what is happening. So my questions will be: how do droplets grow? How do they interact with the flow? And what about the microphysics? And is there a way to do well-defined experiments where we can look at it? Where we can look at this portion of a cloud, and we all know that one of the important issues is the change in height of that proportion of the cloud. And if you want to go in nature, this is a typical example where nature is doing that. So this volcano just took a piece of a cloud and is rapidly moving it upwards. And we can observe that piece of a cloud and see how rain is formed up there. And that is one of the possibilities. You can also try to do measurements in the clouds by helicopters, balloons, whatever. Or you go into a lab, you take a light scattering cuvette, which is 5 milliliters, put it in an aquarium, and watch it. And the movie that you saw in the beginning is exactly a movie like that, except that I was cheating, which is the upper part of this movie upside down that you have seen before. Upside down, for me, is not an issue. Because from the point of view of thermodynamics, it doesn't matter whether I look at the demixing and precipitation in the lower phase or in the upper phase. It's completely symmetrical, except that when I'm in the lower phase, then the material which is coming out is lighter than the surrounding material, so it's more like bubbles which are rising. When I go up there, it is droplets which are falling. The physics is completely symmetric, and you get these nice precipitation events. You can follow them very beautifully in the lab and observe what is happening. So this is a different movie. It's a methanol hexane system. This is a phase diagram. It will also go through phase separation to a very, very similar system. The system that you saw a moment ago was an isobutoxyethanol water system. We have done it for microemulsions, polymeric systems. Once you understood that this is generic, you can do it with olive oil and raw spirit. I'm discussing with colleagues who are interested in star atmospheres and exoplanets. So you just list the ingredients of your atmosphere. You tell about how temperature is changing, and you see how precipitation is occurring. The important thing here is, so our typical experiments run over something like 10 hours. So typical timescales for the change of temperatures is 1 Kelvin per hour. Typical ranges where we follow these systems is 10 hours for a single measurement. We see repeated precipitation events, and our timescales are a centimeter. Very different from clouds. but still it has precipitation. Hmm? This was methanol and hexane.
So one of
Okay. So the lower phase had a lot of hexane and a little bit of methanol. The upper case the other way around. When you change the temperature, let me just see. Yes. When you change the temperature, the composition is changing. A change in composition makes for a mass exchange between, or mass flux from into the respective minority phase, so in the droplets. So by that change in temperature, the droplets in such a phase grow. And once they are large enough, then gravity will make them lift them upwards. That's what we observed. Okay.
So for cloud.
So for cloud, it would be so my picture for cloud is that you have humidity and air. So this is nitrogen and water and some other stuff. It's two fluids. This water package is moving up a hill, or you are going up a cold front. So you're rising in height. There's a diabatic expansion. A diabatic expansion makes that the system cools down. Cooling down in a phase diagram means you go deeper into the miscibility gap. You feed your droplets. They become larger until they undergo coarsening. They undergo collisions, possibly, until they are so large that they feel gravity and then they fall. I will come back to the physics and explain what is happening there.
Clouds are also in a turbulent environment, and that's going to lead to the droplets running into each other and growing that way. Is that in your
I will also come to that point. Or I'm happy to have a question on that in the very end.
They were not homogeneous.
That might also be true. So even these things are not necessarily homogeneous. So let us see now. So for me, the first issue is to decide about my temperature protocol for my experiments. I want to build it from the bottom. So what I want to do is I want to adjust so what I explained now is that the temperature changes lead to a concentration, so a change of concentration, and so they induce a mass flux between the surrounding medium into the droplets. The droplets grow. And this mass flux there can be calculated based on the phase diagram. What we will do is we will adjust our temperature protocol in such a way that the equilibrium mass flux is preserved. The response of the system can be anything. It can be a highly time varying mass flux, but I take my temperature protocol in such a way that when I would immediately relax keep my system in equilibrium, then this mass flux that I need for that is a constant. So that's what I do. It's not what the cloud will do, but this is what I do in my experiments now. Okay, so this is my phase diagram. I go into the miscibility gap. I wait till the system is phase separated, and then I start my temperature protocol. It's a funny function now, which is calculated based on my phase diagram, which tells me about the mass flux. Different mass fluxes, different driving give rise to different temperature protocols, and I can vary that. And then what I see is that I see that big droplets which scatter light arise, system gets turbid, it clears up again, so this means precipitation. Next cycle, where it gets turbid, clears up, and so forth. So that's exactly a picture like that. So it's the initial video, this time in false colors. We decided to average the turbidity in horizontal direction. Reddish means turbid, blue means bright colors. So this is the average in horizontal direction. We put this as a column of pixels next to each other, and then in the course of time, we get these very beautiful space-time plots where precipitation events appear as spikes, and we can measure the time between these events. There's another picture. Here is the precipitation happening in the upper phase, so we can do that for the lower phase. For the upper phase, we can vary the driving, and we can go through our parameter space. And we can measure this time scale, and we can try to understand it. That's what I will be after. I can also look into the system, identify my droplets, follow the droplets, measure their size, and then I get a space-time plot of the size distribution of the droplets. So that is what I also know. So that is my experimental input. And that experimental input gives me enough material to play, and now we want to do theory about that. So the first thing is you vary the shape of your container, or you saw in that movie a moment ago that we have magnetic stirrers in there. So you stir your system, you change your geometry, you vary the flow, and you observe that the period does not change. So apparently convection, at least mild convection, doesn't matter. So even though the droplets are not completely homogeneously distributed, that doesn't matter. The signal is stable, at least the signal that we are interested in, this time scale. So that's stable. So this is typically what the picture that people have. So what we observe now is a relatively sharp droplet distribution, where the droplets slowly grow in time. And then at a certain point, when the droplet size is approaching 30 microns or so, the largest droplets, so the droplets which sit in this tail, start to feel gravity. They fall a bit faster. They fall on other droplets, so they have a substantially enhanced collision frequency. They run off and eat the small droplets. That's a present understanding of rain formation, but it's a qualitative picture. It has never been tested quantitatively. So let us try to see what we can do. So what I should say now, so the first issue would be when you see a distribution function like that, and when you want to know what that distribution function is doing in time, and there's a very well developed piece of asymptotic analysis going back to the 60s, Lipschitz-Schlosser-Wagner theory, which tells us how a size distribution of droplets evolves towards equilibrium. So the issue is that when you take the volume of some droplet I, then its time derivative changes in proportionality with the diffusion coefficient, with some microscopic length scale, few angstroms typically, which takes account of the surface tension of the problem. And then when the radius is larger than some critical radius, which depends on supersaturation, the droplet grows, otherwise it shrinks. So small droplets disappear, large droplets grow. And they do that in such a way that they preserve the total volume of the phase if we are in equilibrium. So temperature is fixed. For fixed temperature, the sum of all these SI dot has to be 0. It's a change of the total droplet volume. You can just insert that here, and what you learn from that is that this critical radius is just the average radius of the droplets. And then you do scaling theory, just as we did for the droplet size distribution, and you get that the average radius cubed grows like sigma d times t. So when you take the time derivative here, then r dot is sigma d over r squared. That's an important message here. People have checked that for clouds, and it's wrong. It doesn't work for clouds, because this process is too slow. On the other hand, this is also not true for clouds, because in clouds, the droplet volume is not preserved. The droplet volume, at least in my experiment, grows linearly in time. So if it grows linearly in time, then you can put that into the scaling theory, and we see a correction factor here, which depends on how rapidly I drive my system, how strongly I drive my system. So that explicitly enters here. And now as a function of this change, we would like to understand what is happening. And so what is happening is that so there's an interesting thing about the distributions. The distribution functions do something completely different. In view of the time, I will skip that here. I'm very happy to show that in the discussion. But in spite of the fact that the distribution function has a completely different physics, and in spite of the fact that we are driving the system, the scaling that when we look at a typical large droplet, then it grows like, then r dot goes like 1 over r squared with some constant which is much, much larger than Lipschitz-Schlosser theory predicts and which we know. And then there are additional contributions, of course, when these droplets are large enough, they collect other droplets, and the collection is just going like kappa times r squared is the Stokes settling velocity of droplets. Psi times T is the volume fraction of droplets. When I multiply that by R squared, which is a cross-section of a droplet picking up something, and this is the volume growth. So the largest droplets in the system, which eventually see gravity, will evolve according to such a law. So we know all these constants now. There's an interesting property. Initially, when the droplets grow, the R dot will grow slower and slower and slower. Then the system will go through a bottleneck until it feels gravity, and then the growth will become much, much faster, very, very rapidly. The consequence of that is this thing takes a finite time, no matter where you start. This goes to a finite time singularity. So you go in a finite time from 0 droplet size to infinite droplet size, and that time is dominated by the time it needs to go through the bottleneck. So the time scale that you need to go through the bottleneck is a time scale which we can take as a test case in order to see whether this precipitation is properly described. And what that tells us is that the oscillation period, so the period between subsequent precipitation events, should scale like psi to the minus 3 over 7. Psi is a parameter that tells us how rapidly the volume fraction of droplet changes in time, so it's our driving, and these are material constants. Okay, we did that with our graduate student, Tobias, together with Michael Wilkinson. We sent Tobias into the lab. He collected tons of data. He compiled them. We plotted the time delta t as a function of psi, double logarithmic scales. We hoped to see a data collapse, and as so often in life, it doesn't appear. And it doesn't appear in this case because clearly, I said that these are material constants. In particular, kappa involves the density difference between the two phases, and initially we are close to the critical point. There's hardly any density difference. After a while, we are very, very far away, so then there's a large density difference. So all these quantities are functions of the distance from the critical point. And we know these functions. I mean, all the material constants are known. They have been measured. If they have not been measured, we measured them. And so what we can do, rather, is we plot now psi to this minus 3/7 times the period as a function of the time. As a function of temperature. Theta is the reduced temperature. And then all these data basically fall on scaling plots. And these lines are not fits to the data. They are eventually the lines that you get by collecting all the material constants. So there is a small uncertainty in here, which is factor 2 or 3 upward. But otherwise there's nothing that you can change here. And that's very, very beautiful, because we varied our driving over 3 orders of magnitude. We saw oscillation periods which vary over 3 or 4 orders of magnitude. And we did the measurements for the lower phase of isobutyrethanol in water. For the upper phase, we did it for the methanol hexane system. It's all the same theory. Basically no fit. It all works perfectly nice. So final step, 2 minutes, is to ask the question, that's a nice experiment in the lab, but where, and what I told you is that there are 2 important things that you want to know about precipitation. One is material constants, and one is this driving parameter, so this driving psi. And this psi that we had is of the order of 1 over hours. So what would a real cloud do? Is it really 1 over hours? Is it somewhere completely different? So is there a chance that that really applies? So we go to the phase diagram of humidity in, this is the cloud point of water in air. So this is a part of our phase diagram. From that we can calculate that the change of composition with temperature is something like 10 to the minus 3 per Kelvin. And now we do a back of the envelope calculation. So we know the slope of our phase boundary. We know the adiabatic lapse, which is 1 Kelvin per 100 meter. And now it can be 2. Don't discuss about a factor 2 here. So let us say it's order of magnitude 1 Kelvin per 100 meter. And then you see that you get very, very small numbers here. So let us take a huge number for the for these wind speeds. The maximum that you can ever reach in a turbulent thunderstorm cloud. What we get is psi in the order of 1 over hours. It can be smaller. It can be an order of magnitude smaller. But it is in the same ballpark as these experiments. And when we drive binary mixtures, no matter what binary mixtures, in this way we observe this precipitation. It always happens on the time scales of the order of this hour. So that might be a relevant parameter also for clouds and for cloud parameterization. And I'm very, very happy to discuss that with people who would have data and could provide me with data for real clouds. Take-home messages. There's lots of new physics in aggregation dynamics. And that's what I'm really enthusiastic at the moment. So there are these non-trivial cutoff functions for dew. There were non-trivial exponents there also. And there is non-trivial crossover between droplet growth, which in itself is a non-trivial thing, where we observed quite a bit of funny behavior now to gravity. And that can be modeled, and we can set up well-defined lab experiments where we can aim for quantitative modeling and then hopefully nail down parameters that are really relevant and that might be important then also to take into account when you do parameterizations, for instance, for clouds. It can be generated in a relatively straightforward way to Grapple. I doubt that it's easy to go to snowflakes. On the other hand, when you want to go to marine snow or to other aggregates, for instance, hydrogen crystallites in liquid helium, that can be done. And this physics is also quite intriguing. I'm doing that with a low temperature physics guy at the moment. And with that, I would like to thank you for your attention.
Just one general question. I would like to know your opinion about the possibility to tackle this kind of problem, this subject, from the standpoint of kinetic theory, for example.
Okay.
So I was wondering whether, for example, the theory of granular gases may somehow give some...
So the theory of granular gas is exactly what I would like to do for the Grapple. So the Grapple for me is so what I do there is I generate aggregates, which is the theory that I have. And for that it is important that we did these polymeric experiments. So I told you that we can also do these experiments for polymers. And the issue about polymers is that the aggregates that we get are little plastic balls. They are not fluids. So they are gel particles. And when these gel particles are sticky, then these particles which are running around, these are small particles which are running around, they're a little bit sticky, they can collide. And that is exactly where I see connections to the theory of granular dynamics.
Starting from kinetic theory would give you the possibility to grasp what the hydrodynamics is of this system, not just a phenomenological theory, but it would be founded on a more kind of fundamental description.
I'm very happy to discuss about that. I mean, so we in my group. I mean, the focus on this talk was on the experiments because I think that they're very important for climate modeling. But we also do kinetic theory for granular systems, as you might know, and or granular motors, large deviation theory, and I'm very happy to discuss that and look into it.
I think if you're interested certainly in rain and probably clouds, but you want to look at the Smolakowski equation for collisions, and also it's important to take into account turbulence.
Okay.
And I have some stereophotography of raindrops I'd like to discuss with you afterwards.
Yes. Okay. Let me give a brief answer to that. So I'm cooperating with a few people in Eberhard Bodenschatz group. They have a huge wind tunnel where they want to see the collision of cloud droplets. They feed in droplets into their wind tunnel, and as far as I can see, it's very, very hard to find collisions. So my estimate would be as long as gravity is not important, then the growth mechanisms just by aggregation of supersaturation are absolutely dominant. Once you're at a level where gravity is important, then gravitational settling and these turbulence effects might go together. But that is once you have passed the bottleneck. and that is changing some small details in how the droplet size becomes large, but that's a higher order correction to this model. But that's my point of view at the moment. I mean, I'm happy to discuss it. And
I think the Stokes number is the key thing here.
Yes.
When that's small, then
Yes,
to
it's
be
small.
fine, but in rain, it seems to be often quite big. So
I mean, but for rain droplets, I mean, when you're at the 50 or 100 micron level,
yeah.
but I'm speaking here about how you go from 10 to 25 or so.
Yeah.
And for that, the Stokes number is still small.
Small.
I know.
I'm absolutely no expert in this field, but I'm just wondering, does dust play any role?
Yes, of course.
You don't have dust in your experiment, right?
No, there's no dust in this experiment, and that's so you see, there's different physics happening on when you are far beyond the bottleneck, and there is interesting and different physics happening for the activation of droplets when you're at this very small droplets. So droplets can never go to zero size when you have dust in the atmosphere. And then these activation issues of droplets is also something that should be included. I believe it can be.
It should have something to do with the cut-off of your scale at some point.
So basically, when you think about this growth model, R dot, then I told you that the droplets, R dot is a function of droplet size, looks like that. And here I would expect dust to be important. Here I would expect turbulence to be important. In order to come down here, these particles have to be activated, so they have to grow by diffusion. Activation is a different issue. So once you have activated, then you have to grow through here, and that's the time scale I'm after. And you see, this is what the chemists and colloidal people and a lot. And there's a huge community of people who are working on that, in particular in cloud chemistry. And there is a turbulence community working on that. And this is a length scale which sits right in the middle. And I believe it is a very, very important window to look at.
Can you explain why it is
In 2 dimensions, you found that the so-called white area is decreasing as time to the power minus 1/4. Is it?
That was a prediction. I see minus 0.3 and minus 0.15 for the numerics and for the experiments.
In 2 dimensions, for the vortices, there are experiments of tabling showing that the number of vortices decays as time at the power minus 3/4.
Okay.
They managed to find they found an analytical derivation of this exponent, which might be interesting. But as far as I remember, they have not considered the gradient flow.
Okay.
And my question is, in that exponent that you found,
Yes.
the expansion of the drop without coalescence.
Mm-hmm.
Is it an important factor in the exponent? I mean, it's
Let me think about it. No, I believe that exponent is entirely coming from the coalescence.
it probably should be.
Yes, on the other hand, I mean, I should be very careful about that statement because at the moment, I mean, the problem is that this is an exponent which is varying over at least a factor of 2, and I have no clue why it is not universal. So there has to be an interesting coupling of that exponent to the physics at the small scale cutoff, and that is what we verified numerically. I mean, that's a physics that the small scale cutoff can change the exponent, which is the place where we have to look now. I cannot tell you at the moment why it does it. We are fighting with that. And when anybody has ideas about when you do a scaling theory, how the physics of the small scale cutoff feeds back into the exponents in a systematic way, then I would be very, very happy to learn about that.
So
maybe I ask the public, is there any more question that cannot be discussed over a glass of wine? If not, I would propose to thank all the speakers of the afternoon.